let's talk about our intermediate approach to our bill splitting problem. How does an intermediate person write this code? Well, an intermediate person might add a little bit more flourish or a little bit more mechanics to their code. They might add type hints and documentation. One thing that we were doing earlier that was a little ambiguous as to whose responsibility it was effectively who is responsible for actually converting our bill, which was in dollars as a floating point value, in order to perform arithmetic operations with integers. Should that happen outside of my function? Should that happen inside of my function? And well, what we can do, instead of writing a user manual, a very explicit user manual, we can actually add type hints to our code. Now, before I talk about type hints, I want to reassure you, this code is all exactly the same as it was before. We've added just one thing. We have added the fact that our bill is going to be converted to an integer internally, but how do we let our users know that we are doing this? Well, we can use things like type hints and docstrings. Now, our type hints here are here to point out to our user the bill should be a floating point value, the guests should be a list of strings, and our random state should be an instance of our random object from our random module in Python. Then we return a dictionary of strings mapping to integers. And to give these values a little bit more unit information, we can supply a docstring here. And we can say that we split the bill specified as floats in dollars, and then we return a dictionary of payments that map each guest to an integer value representing how many pennies or how many cents they paid. We can even include a doc test here, and you can see if you've used the Python REPL, all I would need to do is actually run my split bill function, which I've defined here, and we can specify a bill. In this case, our total bill was $3, and we had 3 guests, A, B, and C. Now I can actually execute this doc test using the -m flag, and you can see that I can see all of the individual doc tests that were run, and then a summary saying which of these passed and which of these failed. In this case, we made a correct assumption about our output, about how we're going to split our $3 into 3 sets of 100 pennies amongst our guests. Now, the nice thing about the doc test is that not only is it a test in and of itself, but it also provides some sample usage to your end users. So all they need to do is look at the docstring and they can see how this function is supposed to be used. Now, an intermediate user often discovers that the process of writing tests improves the code itself. And so if we take the same function that we just wrote and we start feeding it into PyTest, well, we can use our hypothesis package in order to help us find edge cases and corner cases, things that we might not have come up with on our own. This is what hypothesis is excellent at doing. And so if instead of just writing a test, we also build inputs for that test using hypothesis, well, we could envision a different style of test. Instead of just passing the same exact inputs that our program is going to use, we can abstract that one level and we can build inputs that then lead to the inputs for our actual function call. So in this case, we're going to build a dictionary of bills, and these dictionaries will be keyed on an arbitrary object. The reason we're keying on an arbitrary object is, well, as an intermediate user of Python, you may know that, well, assuming that all of our end users are going to use strings to represent their guests might be a very strong assumption. And so instead, we're going to say that our end users may use any valid hashable Python object. And so I'll just here use the basic Python object to represent this. Then the values that are paired with each of those guests are going to be floating point values. And this is the part where hypothesis is going to make us think a little bit deeper about the problem here that we have at hand. For example, I'll work my way from right to left. For example, well, I have never gone to a restaurant and seen a negative value on the bill. If I did, I would be very happy because that means the restaurant is paying me to eat there. And as long as the food was okay, I think I'd be happy with this deal. Additionally, well, hypothesis, since it's working with floating point values, infinity is a valid float in Python. And so this is one of the corner cases where our code might break or our test might break, because when we think in terms of dollars and cents or going to a restaurant and splitting a bill, we never encounter the scenario where we have an infinite bill. Additionally, in the same realm, we're not going to use not a number, which again is a valid Python floating point value. And so we never see a bill and it says not a number. If that was the case, I would probably be excited and just get up and walk out. Finally, we're going to set an arbitrary max value. We can think, well, computers can only add up such large numbers, such large floating point numbers in Python specifically, that we might get an overflow error. And in order to avoid this, we can make the assumption that if our code works, or if our bill splitting function works with any input under 100,000, it will likely work with any input larger than that unless we hit an actual overflow. Now, we'll also pass this min size. Now, this min size is related to the dictionaries that we are constructing, not to the floating point values. And we're saying that, well, whenever we go to dinner, or whenever we split a bill, we're splitting it with at least one person. In our testing, we are never going to split a bill with 0 people. And so let's go ahead and rewrite these tests as our intermediate user using hypothesis. See that the formulation is largely the same as our PyTest tests. The only change that we've provided here is our use of our given decorator. Now, we test our split bills, we implement our smoke test exactly as we did before, and you can see we're being very explicit, lining up our actual payments with our expected payments here. Then we have our total bill. And in our total bill, we're computing, right? Remember, our inputs are one step removed from the inputs that will feed into our bill splitting function. And so our total bill is going to be the sum of all of the dollars in our bill, and our guests are going to be all of the keys from that dictionary. We can test different aspects of our function now, our bill splitting function. If our smoke test is designed to give us just a kind of proof of life signal of, is this code working as we expect it to or not? Well, if it is, it might be in our best interest to go and do more specific tests in this case. And so our specific tests are going to make some assumptions, or make some assertions, I should say, about the inputs and the outputs. For example, the payments.keys, remember, this is my output. So if you are being told that you need to pay this amount, well, you should have been present at the meal or at the dinner. And so this is just making sure that if you went to dinner, you're paying part of the bill. Then we can also assert that we are actually paying the restaurant the full amount of money that is owed. Finally, depending on if there's 0 or 1 or more guests, we might want to run a couple of different scenarios or test different scenarios, such as, well, if there's 1 guest, we should assume that if we count the number of unique payments being made, there should just be 1 payment. And if we are counting it, we should have the total bill mapping to that single value. If there is 2 or more guests, well, we might say we have 2 scenarios then. If there's 2 or more guests, we might split the bill evenly, or we might split the bill unevenly. And that is what the 2 cases here on either side of this or are doing in that order. Finally, we might think, well, what if we have a bill of some finite value, but we don't have any guests? You can think that this wouldn't come up in kind of the logical use of this code, but it might come up in the automated use of this code. And so we might want to assert that this code here will actually raise an exception in this case. And so we can do all of that using the combination of PyTest and hypothesis. And hypothesis is going to help us find out those edge cases that we might not have thought of on our own. Now, for an intermediate user, the writing of the test and the thinking through of the test will often lead to improvements to the code itself. You can see that with this code, I can actually rewrite it. I can rewrite just a couple lines of it. For the most part, it is the exact same, but I can also say that, well, in this case, if the bill is $0, well, my output is going to be everyone who is present is going to pay $0 in that case. And that was one of the edge cases that Hypothesis helped me uncover. Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.